Hello students, in the earlier presentation we have discussed about what is a d block element, its general electronic configuration, atomic and ionic radii, ionization potential, atomic volume and density, melting and boiling points. In this presentation you will know about the two important properties of the d block elements. One, that is variable oxidation state, and one more property, it is magnetic properties. First we will know about the variable oxidation states. In the periodic table, each block, S block and P block elements shows one of the characteristic oxidation states, but our D block elements shows variable oxidation states, means more than one oxidation state. Almost all the elements, that is D block elements, shows variable oxidation states except the first and last member of each series. How many series we have? 3 series. 3D, 4D, 5D. Next comes the question, why this D block elements shows variable oxidation states? It is due to the presence of unpaired electron present in the d orbitals or incompletely filled d orbitals. Due to the presence of unpaired electrons or incomplete filled d orbitals, these elements show variable oxidation state. And if you see the energy difference between ns and n minus 1 d orbitals, it is very less. And the energy difference between the successive ionization potentials values is also less. These all things makes the D block elements to show variable oxidation states. Next, we will see the relation between how the outer electronic configuration will affect the oxidation state. We have taken the first transition series, that is 3D series, scandium to zinc. This is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. As we know, scandium, it is having the general electronic configuration argon. I have not written the argon, it is common for all the elements. And for scandium, the general outer electronic configuration is 3D14s2, and it shows the oxidation states of +2 and +3. For titanium, it is 3D24s2, oxidation states +2, +3 and +4. For vanadium, the electronic configuration, it is 3D3, 4s2, and oxidation states are +2, +3, +4 and +5. For example, if you take the chromium, which is the element of having stability of half-filled condition, that is 3D5, 4s1, it shows the oxidation states of +2, +3, +4, +5 and +6. If you come to the next member, that is Mn, manganese, atomic number 25. Its configuration 3D5, 4s2, and its oxidation states how many here? 2, 3, 4, 5, 6 and 7. Next element is iron, 26, 3D6, 4s2 and +2, +3, +4, +5 and +6. And for cobalt, it is 3D7, 4s2. It shows oxidation states of +2, +3 and +4. And for nickel, the oxidation states which it has shows, it is +2, +3 and +4. And for copper, it is the electronic configuration which is again stable due to the completely filled d orbital, that is 3D10, 4s1. It shows an oxidation states 2, +1 and +2. And the last element, as we already told, this will be showing only one oxidation state, that is +2. And if you see the oxidation states in the earlier slide, here the oxidation states, one oxidation state will be differing from the other oxidation state by only 1 unit. And if you see up to Mn, that is manganese, 3D subshell has only unpaired electrons, but after manganese the pairing will be started. That's why here if you take all the elements of 3D series, the minimum oxidation state of any element, it is equal to the number of electrons in the s orbital, and the maximum oxidation state, it is equals to the sum of electrons in s and also dn orbitals. Okay, minimum oxidation state is equals to the number of electrons in the s orbital, and the maximum oxidation state, it is equal to the sum of electrons in the s and d orbitals. The next 5 elements, that is after manganese, the 3d orbitals, as we told here, they used to have a paired d orbitals, and in this case we have to take the minimum oxidation state is again the number of electrons in the s orbital, but the maximum oxidation state is not related to the electronic configuration, which we have told that the maximum electronic configuration up to manganese, it is equal to the sum of electrons of S and D. That will not be applicable after manganese. And here, in order to predict the oxidation states or maximum oxidation state for 4D and 5D series, it is +8. This +8 oxidation state is seen in two compounds. One, it is RuO4, ruthenium tetroxide, and OSO4, that is osmium tetroxide. These elements show highest oxidation state of +8. Now we have known about the 3D series elements. Why? Because their electronic configuration was exactly known, and how this electronic configuration related in showing the different oxidation states, that is variable oxidation state. Now we will discuss how this oxidation state are relative stable, nothing but relative stability of oxidation states of transition elements. Here, the stability of a particular oxidation state, it is related to the extra stability of 3D0 or 3D5 or 3D10 configuration. Nothing but for any element in its oxidation states, whether it may be +1, +2 or +3 or +5, +6 also, if that oxidation state makes the gaining of electronic configuration of either zero filled 3d orbital or half filled 3d orbital or 3d10 orbital or 3d10 configuration, this condition makes that a particular oxidation state will be stable for that element. For example, if you take iron of atomic number 26 and its electronic configuration, it is argon 3d6 4s2. Here, if you take iron in the +3 oxidation state, here in +3 oxidation state, the electronic configuration of iron is 3d5. Whereas if you take iron in the +2 oxidation state, it is gaining the configuration, it is 3d6. As we see here, 3d5 is a half-filled condition, and 3d6, it is not a half-filled condition, one electron more than half-filled. That's why compared to the +3 and +2, +3 oxidation state of iron, it is more stable. One more example, if you take manganese in the +2 and +3 oxidation state, in +2 manganese have the electronic configuration as 3d5, and in +3 oxidation state it is 3d4. This is a half-filled condition. That's why this particular oxidation state is stable for manganese. And if you see the 4d and 5d series, the higher oxidation states will be more stable than 3d series. What is the higher oxidation state shown by 4d and 5d? It is +8, which we have discussed in the earlier slide now. Next property, ionic and covalent character. As we told, two types of oxidation state. One, it is lower oxidation state and higher oxidation state. Generally, lower oxidation state elements will form ionic compounds. Why? Because the tendency to form ionic compounds decreases as the oxidation state increases. For example, if you take manganese in +2 oxidation state, it forms ionic compound, that is MnO, manganese oxide. Whereas in the manganese +4 oxidation state, it forms MnO2, which is intermediate between, that is ionic and covalent character. Next one, it is acidic and basic behavior. Generally, the acidic character of oxides increases with increase in the oxidation state. If you take the example of manganese, which is showing oxidations of +2, +4 and +7, manganese oxide, which we have told it is ionic in nature, it is found to be basic, and MnO2, which is showing +4 oxidation state, it is amphoteric, and the highest oxidation state, that is Mn2O7, it is acidic in nature. Next, relative stability with respect to oxidizing and reducing nature. Generally, the higher oxidation states will be acting as oxidizing agent. At this point, I want to remember you about what is an oxidizing agent and what is a reducing agent. Oxidizing agent is nothing but which one will be undergoing reduction. Reduction means loss of oxygens, gain of electrons, gain of hydrogens, okay, or that is the reduction. Generally, any compound which undergoes reduction will be said to be an oxidizing agent, and exactly the opposite case for reducing agent. One of the important compound which is acting as a strong oxidizing agent, it is FeO4 2-, which is acts as a strong oxidizing agent which oxidizes ammonia to nitrogen. For oxidizing ammonia to nitrogen, here the generally used oxidizing agent, it is FeO4 2-. Okay, this completes the variable oxidation state and its relative stabilities. Next, we will move on to the next property of D block elements, that is magnetic properties. For example, in order to know a magnetism of any substance, we should place that particular substance first of all in the magnetic field. Depending upon the response of that substance or a compound with respect to magnetic field, we can classify that particular substance as two types, whether it may be a paramagnetic or it may be a diamagnetic. Nothing but here, when magnetic field is applied to the substance, mainly we will see two types of magnetic behavior. One it is, we told it is diamagnetism, another one it is a paramagnetism. Now we will know what is diamagnetism and paramagnetism. Diamagnetic substances are magnetism is a property of a substance which will be repelled by the applied magnetic field, whereas the paramagnetic substance will be attracted to the magnetic field. And if the substances, if they are attracted very strongly with respect to the magnetic field, then that type of a compounds or substances called by a special name called ferromagnetic. In fact, this ferromagnetism is an extreme form of paramagnetism. Most the transition elements which we have discussed and their compounds will show paramagnetism. Nothing but these will get attracted with the magnetic field. Then why this transition elements shows paramagnetism? The same reason again comes into the picture which we have discussed in the variable oxidation states, that is the incompletely filled d orbital or unpaired electrons in the d orbitals. That is, paramagnetism arises from the presence of unpaired electron, and what happens, this each electron will be contributing a magnetic moment. Okay, each, for example, since these deep transition elements used to have unpaired electrons, these unpaired electrons used to behave as a small bar magnet and makes that particular compound or a substance to attract with the magnetic field. Since this particular unpaired electrons gains a magnetic moment, then how we can calculate the magnetic moment? The magnetic moment of any transition element or a compound given by assuming that there will be no contribution for orbital magnetic moment. Okay, for example, if you take any atom and if you have a nucleus at the center and the electrons will be rotating around the nucleus, that electron which is revolving or rotating will be having orbital magnetic moment. Along with that one, since each electron will be not only rotating around the nucleus, it will also spin around its own axis called as which will be gaining the spin magnetic moment. Nothing but here, for example, if you want to calculate the magnetic moment of any element, we have to take into consideration of both orbital and also spin magnetic moment. Here, this orbital magnetic moment contribution, it is less. That's why we are considering only spin magnetic moment. By using that spin magnetic moment, we are calculating the magnetic moment, that is spin magnetic moment mu s, generally magnetic moment denoted by the letter mu s, will be calculated square root of n into n plus 2 bm. Bm is a unit for magnetic moment, that is Bohr magneton. And here n represents the number of unpaired electrons in that particular transition elements. If you know the number of unpaired electrons in any transition element, you can easily calculate the magnetic moment by substituting the number of unpaired electrons in this particular equation, and you can get the magnetic moment. See here, this is a pictorial representation how the particular substance behave with the magnetic field and without magnetic field. For example, if you take any substance, if it is a paramagnetic substance, in that substance without any magnetic field, these particular electrons or magnetic moments are randomly present. Once you apply the magnetic field for this particular substance, nothing but in presence of magnetic field, all the electrons will be aligned. Most of the magnetic moments will be aligned in the direction of application of magnetic field. If you assume the magnetic field applied here in this particular direction, okay, I will also show here upward. Here most of the magnetic moments, these are aligned to in this particular direction, except here some of this one and this one, these are present in the opposite condition. And if you take in the ferromagnetic substances, if you take the ferromagnets, here also all the electrons, some will be somewhat orderly arrangement will be seen for the substance which used to show ferromagnetism. Some will be aligned, some will be opposite. But this type of substances, when placed in a magnetic field, all the magnetic moments will be aligned in the direction of application of magnetic field. Okay, in the paramagnetism, maximum alignment will be there, not total alignment, whereas in the ferromagnetic substance, total alignment of all magnetic moments. And if you see in the diamagnetic substances, okay, all the magnetic moments will be present in the opposite direction of application of magnetic field, or the magnetic field will be cancelled. Whatever you are applying the magnetic field, no, that will be cancelled with the opposite alignment of magnetic moments in diamagnetic substances. Now I have taken here the 3D series elements in the different oxidation states, and we have shown their particular configuration: scandium 3D0, titanium 3D1, like that, zinc 3D10, and we have also shown here the number of unpaired electrons present in this particular configuration, and we have calculated the magnetic moment by using the formula mu s is equals to square root of n into n plus 2. We have got this value, and these values are in good correlation with the observed values, that is by measured values by using the instruments. And if you see the paramagnetism, first it increases in any transition element series, and then it will be decreases. The maximum paramagnetism, it is seen around the middle of the series. For example, if you take from scandium to zinc, here we will be generally seeing the maximum paramagnetism in the middle, that is manganese iron. Okay, here the first the paramagnetism will be increased, and then it will be decreased. Okay, this is about magnetism of transition elements, and also a variable oxidation state, one of the most important properties of transition elements. Thank you.